Hi, students, Cedarville University. It's Mr. Wagner here. As you remember, we are having a virtual class today, so um, let's get started. And remember, if I'm going a little bit too fast for you, feel free to stop and pause the video. You're welcome to do that. Also, whenever there's a video or I reference a video, you can find a link to that video down in the description down below. So you know how I add videos to our lessons. You can watch those, and some of them, I'm telling you, are critical for your understanding. So make sure you are watching those videos. It's going to be very helpful. Okay, so first off, we're talking about the electromagnetic spectrum, right? Our larger topic is light. First thing we need to know is that the sun emits all wavelengths of the electromagnetic spectrum. The sun makes radio waves, the sun makes microwaves, the sun makes infrared waves, the sun makes visible light, ultraviolet waves, X-rays, gamma rays. The sun does it all. But remember, we said that the sun gives off the majority of its radiation in visible light, which I think is pretty cool. The ionosphere reflects a large portion of those waves back into space. So this is, again, one of those kind of things where you think to yourself, wow, is that just a matter of chance, or is that our created world with an intelligent designer that's protecting us from gamma rays and microwaves and ultraviolet waves, because the ionosphere reflects a lot of that stuff back into space. And sometimes when we see our ionosphere interact with some of the sun's waves, we can call that the auroras, the aurora borealis, the northern lights. And that's when our ionosphere is interacting with the rays from the sun. A large solar flare creates enough electromagnetic energy to temporarily disable electromagnetic communication on planet Earth. The video that would be right up here talks about that. I think it's like a minute and 90 seconds, or I'm sorry, a minute some seconds. But in the past, and what will happen again in the future, is sometimes the sun gives off a large coronal mass ejection. So that's this kind of circle right up here. And those things head towards Earth, and it makes a solar storm. It's not much that we can see because it's like all the wavelengths that are not visible to us. But it interacts with our atmosphere, it makes the auroras, but sometimes it knocks out communication from satellites to planet Earth, so it could knock out GPS. It could knock out cellular communication for cell phones. It could knock out TV. It could knock out internet signals on one side of the Earth. It could be absolutely devastating. And I think it probably will happen again in the future. I just hope it's not too soon. So take a moment, watch that video. I think you'll find it kind of interesting. And just to let you know, the information about the ionosphere, the information about auroras, that is not testable information, but it's certainly good to know. Also, radio telescopes like this one right up here. Radio telescopes, they actually see the radio waves and not the light that we see. So they can see gamma rays, they can see X-rays, they can see all the wavelengths that we cannot see. All right, so let's go. Here's our recap of the electromagnetic spectrum. First off, how are ultraviolet waves different than microwaves? Ultraviolet waves are different than microwaves because they have a different frequency. Here's microwaves right here, low frequency. Here's ultraviolet waves, high frequency. Other than that, what's the difference? Nothing. They travel at the same speed, which I think is another question that I was going to ask. But just the frequency is the difference. Which color of visible light has the shortest wavelength? Okay, well, let's look at this. So here's visible light, and we're trying to find which color has the shortest wavelength. Well, over here we have long wavelengths. This is red. It's got a long wavelength that goes Roy G. Biv. Red, orange, yellow, green, blue, indigo, and violet. So which one's the shortest? Violet. Why might the sun be dangerous to communication? The sun gives off all these things, the radio, microwave, infrared, visible, and we communicate with microwaves. We communicate with radio waves. And if the sun is interacting with that, that can be kind of dangerous. There's a video about the electromagnetic spectrum, just kind of a recap on how the electromagnetic spectrum works. I would encourage you to watch that. It kind of clears things up, hopefully. Now on to kind of a newer, I shouldn't say a newer phenomenon, but something that's kind of interesting. I apologize. There's a lot of videos. This first video is making the argument that electromagnetic waves or light waves, they can behave like particles of matter or they can behave like waves. That's called the dual nature of light. It can be both a particle and a wave. But the thing is, it's actually none of those. But it's both of those. Light is special. Light is different than anything else. Scientists still don't fully understand how light works. And remember, we said that when Jesus calls himself the light of the world, he didn't say, I'm like light. He says, I am the light of the world. Light has a dual nature. It can be both matter and energy. And that absolutely baffles scientists. The next video that goes along with this is Dr. Quantum. And Dr. Quantum talks about shooting electrons at a screen and discovering interference patterns. We talked about what interference is. Well, guess what? Light behaves the same way, and they've done the same experiment with light. I really encourage you to watch that video. I got to be honest, there's a tested question directly from that video of Dr. Quantum. So I highly suggest that you do watch that one. Okay, so let's talk about what happens when light strikes an object. When light strikes an object, it can do one of three things. Light can go through that object, so that means transmitted. You can see that in the picture right here. Light can be transmitted. Light can be reflected from the object or bounced off. All right, we know what reflection is. That's from previous lessons. We know about reflection. Or light can be absorbed, right? And here's the deal. It says, are there any surfaces where 100% of the light can be absorbed? You don't have to watch this video if you don't want to, but it's about a paint called Vantablack. And this paint actually absorbs 99.9% of the light that hits it, which could be kind of cool because if you're shooting radar waves at it, it's not going to bounce radar waves back. If you have a jet in the military and you want to paint it Vantablack, no radar is ever going to see it because it absorbs radar waves, which are a form of radio wave or microwave. But the key points here is that light can be transmitted through something, it can be reflected by something, or it can be absorbed by something. Okay? Can you think of a real life example? A window, transmission. A mirror, reflection. Absorption, a black car. It's going to absorb all those rays. Let's continue. When light strikes an object, it's going to reflect, usually, or it could go through, be transmitted, or it could be absorbed. There's two types of reflection. One type of reflection is diffuse reflection. Take a look at this. Pretend that these are laser beams, right? These laser beams are hitting a surface. Let's say it's like carpet, or we could say it's clothing. The surface of carpet, the surface of clothing, the surface of cotton, the surface of wood, they're all kind of a bumpy surface, so the laser beam hits it and it scatters the light. It goes all over the place. Whereas with specular reflection, that laser beam hits the flat surface. Maybe it's a very still pond. Maybe it's a mirror. Maybe it's the back of a spoon, but something that's really, really smooth. And the light hits it and it bounces off in specular reflection. So that is like in straight lines. Okay, so diffuse reflection, it's when an object strikes an object, bounces off in all different directions. Pretend you had a laser pointer, you shine it at the ceiling tiles, it bounces in every direction. But if you hit a smooth surface like a mirror, that's regular or specular reflection. And let me see here, let's move me around. Specular reflection is reflection where light waves bounce off of an object at a predictable angle. We talked about this before. The angle of incidence equals the angle of reflection. So if this is 45 degrees, the angle of reflection is 45 degrees. It typically occurs with a flat, smooth surface. Here's something that's review, right? This is review for us. We talked about waves and how waves behave. Now we're talking about refraction of light. We know about refraction. Remember that refraction is the bending of a wave as it changes the speed when it exits or enters a new medium. So here's some light, right, going through some glass, and the light is going to slow down when it goes through a new medium. In that way, light actually kind of acts like a particle, right? Because it's got to go through something, which slows it down. Here's another image of refraction. And here's another image of refraction. Notice you can see a pencil and it looks like it's broken, but it's really not. It's just because of refraction. Okay, now on to some light and color. This is kind of a fun thing. When light is responsible for the presence of color. I mean, think about it. If you're in your dorm room and you turn off all the lights and there's no windows, can you see the colors of anything? No, you can't. Light is responsible for color. If there is no light, there is no color. So it says go into a dark room, try to identify the colors of different objects. You can't. Imagine you're driving around at night without your lights on your car. Can you identify the colors of the cars around you? You can't, because light is responsible for color. White light contains all the colors inside of it. So just in this prism up here, look, they're shining white light in this prism, and what comes out? All the colors come out of white light. White light contains all the colors. The color black absorbs all the wavelengths of light and reflects no wavelengths of light. So think about this here for a second. Let's just suppose you're shopping for paint at Lowe's. And if you're shopping for paint at Lowe's, when they have all these paint swatches here, are they in a dark area? Nope. They're in a brightly lit area. Why? Because the colors are more prominent. You can see colors better under bright light. If there is no light, there is no color. Two things to take away from the slide. No light, no color. The second thing is that white light contains all the colors in it, which is mind-boggling. It's kind of baffling. So how does light and color behave? Well, let's take a look at this. Oh, and by the way, there is a video that goes along with that one. It's a song, and it's a great song for you to use in your classrooms in the future. It says the color, it says if, it should say of, the color of different objects is determined by the wavelengths of light that the object reflects or absorbs. So look at the bananas here. The bananas really are not yellow. And right now you're probably confused. You're like, what? The bananas are yellow. Well, actually, the bananas are green, blue, and violet, and orange and red, because the bananas are absorbing all those colors. But there's one color that the banana is not. It's yellow. Because yellow from white light, because remember we said white light contains all the colors. The white light has all the colors hitting the bananas, and the bananas are rejecting one color. That's yellow. It's shining that one color back. So therefore, when we look at the bananas, what do we see? We see yellow bouncing off of the bananas. So the bananas look yellow, but they're absorbing all the other colors, right? So like when it comes to the apple here, it says a red objects absorb all the colors except for red. So here's white light from the sun. It's hitting this apple. The apple is absorbing violet, blue, green, yellow, orange. It's absorbing all those colors. But one color is being reflected, this red. So therefore, the apple looks red to us. It's kind of a weird thing. So yellow objects absorb all the colors except for yellow. Red objects absorb all the colors except for red. But what do white objects do? That's a good question. If you had a white object, let's say like a white Corvette, okay? How is light reflected and absorbed by these cars? Well, remember the color white is actually all the colors combined. So white light is all the colors combined, which is kind of baffling. So here when you're looking at the Corvette, what colors is it reflecting? All of them. It's reflecting all the colors. What colors is it not reflecting? None. It's reflecting all of them. But if you look at the black Corvette over here, what colors are the black Corvette reflecting? None. It's reflecting no colors. The black Corvette is absorbing all the colors. I got to stop the video here for a second because I can only upload 15 minutes at a time to YouTube. That's all my account allows me to do. So we're going to pick up here in the next video, which is linked down below.